Hello students, in this video we'll prove the second part of the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus Part 2 says the following. It says if f is Riemann integrable on AB and continuous at a point C on AB, let's say C is in the interior, doesn't have to be, then the function f capital of x, which is the integral from a up to x of f of t dt, is continuous on the interval AB and differentiable at C. With f prime of C is equal to little f of C. Okay, great. Of course, I need to assume that f is continuous at that point, so that makes sense, that f of C makes sense. So how do we prove this? Well, the first part of the proof is straightforward because this function f capital is actually Lipschitz. So notice, proof, f of x minus f of y is equal to the integral from a to x of f of t dt minus the integral from a to y of f of t dt. So if we assume that, and without loss of generality, that x is bigger than y, then this integral from a to y will cancel out. So we're going to have the integral from y up to x of f of t dt. And so now taking the absolute value of this, what does this imply? So the absolute value of this implies the absolute value of f of x minus f of y is less than or equal to this absolute value of the integral, which is the integral from y up to x of the absolute value of f of t dt. But Riemann integrable functions are bounded, so this is less than or equal to a constant m times x minus y. And so that shows that this function f capital is Lipschitz, right? So f capital is Lipschitz, f is Lipschitz m, and therefore it's continuous, f continuous. That's the first part of my problem. Now I gotta look at the differentiability. I want to show that f prime of c is equal to f of c. So now what I can do is I'm gonna use the continuity. I'm gonna let epsilon be greater than 0 and pick delta greater than 0 such that what? Such that if t minus c less than delta, this will imply that f of t minus f of c is less than epsilon. Okay, and so now what I'm going to do is I'm going to look at the difference quotient of this function f at c. So let's look at that. So if I look at f of x minus f of c over x minus c, let's just assume that x is larger than c for simplicity over here. What will this look like? This is going to be 1 over, by the same calculation, 1 over x minus c, the integral from what to what? Well, I go from a to c, then x to c, so I'm going to have a c to x. So without loss of generality, x is bigger than c. We can do the other direction too. That's completely fine. Of just what? Of just f of t dt. So now let me assume that x minus c is within delta. So let's assume, suppose, that x minus c is less than delta, which is the case. I want this to be going to 0. Then what? Then f capital of x minus f capital of c over x minus c minus f of c is equal to 1 over x minus c integral from c to x of f of t dt. And then I'm going to write f of c as what? I'm going to write f of c in a funny way. I'm going to write it as just basic f of c as just negative 1 over x minus c. The integral from c to x of just f of c dt. That's a constant now. So this constant just integrates to nothing. Integrates to f of c, pull the f of c out, you have an x minus c, and the x minus c will cancel. So all total, this is going to be what? So all total over here, this thing over here is equal to, 1 over x minus c, the integral from c to x of f of t minus f of c dt. And now if I take absolute values everywhere, like this, I see that this is less than or equal to what? This is less than or equal to 1 over x minus c, the integral from c to x of f of t minus f of c dt. Now by assumption, since x minus c is less than delta, x minus c less than delta, it says that t minus c is less than delta, so this is less than epsilon. So this is less than or equal to 1 over x minus c, integral from c to x of epsilon dt, and that just will integrate to epsilon. So I've shown that this difference quotient over here, minus f of c, is less than epsilon if x minus c is less than delta. That says that f prime of c exists and is equal to what? This tells me that f prime of c exists and is equal to little f of c, and that's the proof of the second part of the fundamental theorem of calculus. Thank you very much.